quickly with all these options that ECG signal processing using MATLAB, algorithms, classifications, digital filters, methods, and Python. So let's start with the algorithms which we may need in electrocardiogram signal processing. And if we click on the first option, the signal processing today is performed in the vast majority of the systems, ECG analysis and interpretation. The objective of signal processing is manifold and comprises the improvement of measurement accurately. So we need the signal processing so we can improve the ECG from the noisy environment and get the actual patient's data. The noise reduction represents another important objective. So the ECG is recorded using such condition that signal is corrupted by different types of noise, sometimes the originating from the another physiological process of the body. It have different kind of noises in the ECG, so we need to process in it. ECG signals may be recorded on a long time scale, for example, the several days, for the purpose of identifying intermittently occurring disturbance in the heart rhythm. As a result, the produced ECG recording amount to huge data size that quickly fill up the available storage space. So it happens that sometimes we record ECG over a long several days, and we need to identify any time the changes occurs in the heart data. So the signal processing for example, techniques have been developed that heart rate shoot. So if you already aware about the ECG signal is you are from the complete ECG wave. So we need to identify several kind of analysis on that PQR dataset. This will give us some important information about okay. And the further thing, analysis of ECG signal processing and filtering algorithms. If we go to that, the filtering algorithms, so electrocardiogram is common technique for recording an electrical activity of human heart. So obviously the ECG is performed for recording the electrical activity of human heart whenever the heart pumps. Accurate computer analysis of ECG signal is challenging as it is exceedingly prone to high frequency noise. When we record the ECG signal, because of the microvolt signal, it is prone that if high frequency noise could be imposed on that actual ECG signal, and other artifacts due to its low amplitude, because the signal is in microvolts. So the other artifacts like moving and body movement artifacts could be imposed on that, and the remote healthcare systems. um, Computer-based high-level understanding of ECG signal is performed using advanced machine learning algorithms. So we could perform the ECG signal analysis with the machine learning algorithms. But as I say in my previous stream, that we should focus on the basic systems, and we should first evaluate their strength and weaknesses before jumping to the machine learning. I always prefer to not jump directly to the machine learning. So we should not be jumping directly to the machine learning. We should first explore what a common statistical analysis could give us what kind of accuracy level, what are their strengths and limitations of the previous mathematical, because at the end the machine learning is also a mathematical equation, so it is all math. So we should not overkill everything by doing the machine learning. We will not learn what the actual machine learning underhood the algorithm is working, and if we stuck somewhere, we will not be able to improve our machine learning model if we have not explored the previous statistical methods to handle the ECG signal. So the accuracy of the signal to noise ratio, uh, whenever we deal with the noise reduction, we call a term, if you are not already familiar with this term, is SNR, which is signal to noise ratio. So we also talk about the SNR in case of ECG signal. So this paper will be they will analyze the various method for removing the high frequency noise components from the ECG signal and evaluate the performance of several adaptive filtering algorithm. So most of the time in this paper the adaptive filtering algorithm has been discussed. So the result suggests that the normalized least mean square algorithm achieves high SNR and sign LMS is computationally efficient. So basically in this paper, the abstract suggests that they are using various kind of filtering algorithms to get the idea of high frequency to remove the high frequency noises, and the finding of this research paper says that the normalized least mean square algorithm achieve high SNR. On the other hand, the sign LMS is computationally efficient. So these are the common filters they used. Next, moving on to the next paper, the ECG signal processing and heart rate frequency detection method. So as you can see, the digital signal processing and data analysis are very often used methods in the biomedical engineering research. So this topic is specifically for the biomedical engineering field, but if you are working on a signal processing, digital signal processing research field, this could also be a common problem for you, which you can work on. The paper described utilization of digital signal filtering on electrocardiogram. The designing filters are focused on removing supply network 50 hertz frequency and breathing muscle artifacts. So here we introduce two more terms while working on an ECG. We discussed in the while reading the abstract of the previous paper that on ECG there are certain artifacts that imposed on the ECG signal. So what happens that the what kind of artifact there these this paper discussed two more artifacts. The one is to removing a supply network 50 hertz frequency. So whenever the ECG recording machine is working with the 50 hertz frequency, the that 50 hertz frequency from the main AC imposed on the ECG signal, we need some kind of filtration where we can remove that 50 hertz signal. There is another artifact that effect on ECG signal, which is a breathing muscle artifact. So obviously the person is breathing, and that breathing cause your chest to move, and that movement make changes on the ECG signal. So you have to remove that breathing muscle artifacts from the ECG signal before you can actually get the heart rate and the heart related PQRS complex. And the frequency and the breathing muscle artifacts, moreover this paper contained description of 3 heart rate frequency detection algorithms. Okay, so this paper focus on 3 heart rate frequency detection algorithms are based on statistical methods. So yes, that's what I was talking about, that we should first talk about the previous statistical methods before diving into the machine learning. And the differential mathematical methods, so that all or basics algorithms, what that give you the power of using the basic statistical methods and the basics mathematical equations. It will help you to use your resources efficiently. So if you want to implement your algorithm on some edge devices like a microcontroller or some embedded systems, that algorithms will be computationally less expensive, and you can implement those algorithms on microcontroller level as well. So that's why it will give you power to create your embedded devices with higher accuracy levels as well. But if you directly jump onto the deep learning, machine learning, that machine learning algorithms maybe are not capable of fully being converted onto a microcontroller. So that will be a problem for you. Then you have to embed some kind of Raspberry Pi on it, or some kind of computer to tackle these problems. So always explore basic statistical methods and mathematical methods before jumping onto the machine learning. All described methods are suitable for the next simple implementation to a microprocessor. Obviously, if your one more thing I remember, that if your main research area is deep learning, then you should focus on a deep learning. Obviously, then deep learning will be help you more. But if your core focus is not the machine learning, and your core research topic is not the deep learning or machine learning, then you should not touch those areas before you actually understand the problem with standard algorithms. All described methods in this research paper are suitable for next simple implementation to a microprocessor for real-time signal processing and analysis. So obviously their core idea is also to implement those algorithms on a microcontroller or microprocessor level. So this is a total research paper: ECG signal processing and heart rate frequency detection methods. We will go into deeper details of this research paper in the next stream. I don't want this stream to be more long, but because most of the time this stream is assumed to be watched later. And let's see what they actually created. The block diagram, they created a raw signal. They are getting a raw signal and normalize and mean value removing. So this is the first step that you do with the raw ECG signal. After that, you filter the 50 hertz filtering biquad band stop filter, and then breathing filter for 0 to 5 hertz Butterworth high pass. So these filters are most common when you do your heart related signals or any other biomedical signals. And then you find the R peak filtering with the 50 hertz and 20 hertz Butterworth high and low pass filter. There is a sparing mystic signal energy, then you get your digital signal frequency. So in this part, digital signal frequency with filters, and the main noise elements are power supply network 50 hertz frequency. They are saying, if you see this is a raw ECG signal. As you can see, this is very noisy. And let me check if yes. So this is a basic filtration. As you can see, the signal is filtered, and you get your clear peaks. There is the higher peak is a R peak, and then you have other peaks available as well for the QRS complex. So next thing is to okay. So after the basic filtering, the R peaks are detected from the ECG signal. R peaks filtering are necessary for the next heart rate detection. The signal is filtered by high pass and low pass Butterworth filters and cutoff frequencies of 50 Hz and 20 Hz. So the 50 Hz and 20 Hz frequency is used for R peak cutoff frequencies, and both filters are fourth order because of the computing difficulty in the next implementation in a microprocessor. So the Butterworth filter is a fourth order Butterworth filter. That is one more thing that you need to remember while creating a filter. So another the signal after network 50 hertz baseline Vander filter. So they implemented a baseline Vander filter. This is another terminology which you need to check out. So baseline Vander filter is when your actual signal is uh, deviated from your baseline. So you need to apply a baseline Vander filter so that your ECG signal is aligned in a line. Okay. So then they implemented a heart rate detection algorithm. In this part, there are described algorithms for heart rate detection which have been designed in MATLAB. Algorithms can be divided to algorithms based on statistical and differential mathematical methods. The first algorithm is focused on statistical signal processing method like autocorrelation. Autocorrelation method can be used because the ECG signal is quasi-periodical. The MATLAB provides very simple using of autocorrelation method in signal processing, which is very useful for this purpose. The heart rate detection is pretty simple. I had already created a video on it where you can see that we detected the R peaks, and then we count the R interval, and then we calculated the heart rate from that R to R interval. So this is very simplest algorithm to calculate the basic heart rate. Then they explore to autocorrelation of energy signals and thresholding of the energy signals. Let me quickly go down and see what other important factors they had go through with this. Well, the results, the design digital filters and the heart rate frequency algorithms are very simple. The filters have small loss acquired during the stress test. It may be argued that differential computing methods are better for real-time processing implementation. So their findings are summarized that for the real-time signals, the differential computing methods are better. So if you go to the other papers, the real-time QRS detection algorithm, so this could be a next good topic to study on. So I will end this stream for this, and we'll continue this digital signal processing in the next stream. Thank you.